Sequestration coordination compounds, where you have crown ethers and things like that that create a cavity with some kind of ligands underneath, and this cavity is very important regarding which cation you can extract there. So you can design cavities for a given cation, and the size of the cavity is what makes the selectivity. So I thought, what cavity can we have here? Looking at the structure of the surface, the cavity will be more or less the size of the platinum ion underneath. And the platinum atom. And platinum atoms have a diameter of approximately 2.7 angstrom. And if you look at the ionic diameter of lithium, sodium, potassium, and cesium, potassium has a diameter which is very close to that one. So then we realized that we really have not only an effect of the hydration energy, but also a cavity effect. So the place where the cation is going to be attached has a size, and only cations that match very well with the size are going to be strongly retained there. So this is what we expected to see, either this structure or this structure, and then we did some STM, and we indeed could see the cations attached on the surface. What we saw is that this is the way they attach, not this one. And you see here these hexagons, and this is a higher resolution image where you see one cation here, one here, one here, one here, one here. You see the 6 cations surrounding the cyanide group, which would be here and which we cannot see. There is a lot more to say about these STM images, but I am not going to get deep into that because it's going to be. But I tell you, there is a lot of information here which we are working now on, and which is really beautiful. But well, if this idea of the cavity and the size of the cation is important, we have to check it. And we check this by trying with other cations. So this is the alkali cations. We have lithium, sodium, potassium. We have seen that sodium and potassium are the ones which attach more strongly, particularly potassium. But then we thought, well, if we take now a cation with a higher charge, we would expect it to be more strongly attracted to the surface. So we thought of iron, cobalt, nickel. And curiously, when we use iron, which, as you see, has a very small radius comparable to lithium, we couldn't see any iron attached on the surface at all. So these experiments, what we did, we took the cyanide surface, we immersed it in a solution with a cation, then we take it out, we rinse it with water, and we go to a solution where we haven't got the cation. If the interaction is very strong, the cation is going to be retained. If it is not, it will be simply washed away when we rinse with water. And what we found is that all these cations, they are all washed away. And only silver and copper, well, about copper I speak later. First, we saw only silver is retained there. And actually, with silver, you have a huge signal of reduction of silver, which means that we have a lot of silver there. We have not quantified it yet, but we will. And if you look at the radius of silver, it's very similar to that of potassium. And a very interesting result we had with copper. If you look at the radius of copper, it's very small. So we would expect copper to behave similar to iron or maybe cobalt. But when we did the experiment, we again saw that we had a lot of copper. And we could again see copper on the surface with STM. So we thought, why is it that copper does not fit? Because the size is very small. But then we realized that copper 1 is bigger than copper 2 and has a radius very similar to sodium. And actually, we took our electrodes out of the cell and went to a UHB chamber and made some XPS. And this is our copper on our cyanide-modified platinum. This is a copper 1 sample that we tried, and this is a copper foil. And we see that what we get is something that looks very much like copper 1 on the surface. Certainly not copper 2. So what we think, and we know that copper 1, the oxidation state of copper 1, you know it's very unstable one. Copper 1 tends to deproportionate into copper 2 and copper metal. And one way of making your copper 1 oxidation state stable is by making cyanide complexes. So copper cyanide, what you have is copper 1. You don't have copper 2. So it makes sense that cyanide is stabilizing somehow our copper 1 state, and that's why we're seeing it. And this altogether confirms the relevance, the importance of the cavity. But then, this is all very beautiful, but this is a model. And we thought, well, these non-covalent interactions might be relevant in many electrochemical processes at interfaces, particularly electrocatalytical process. So is it possible that this model can be applied to other situations in which cations affect the properties of the electrical double layer? So we went to a very simple thing. And again, we come to model systems. Again, a single crystal. This is platinum 111 without modification, only platinum 111 in sulfuric acid. And I will explain what we have here. This is hydrogen adsorption. Here we have sulfate adsorption. And initially, when sulfate adsorbs on the surface, it adsorbs in a disordered way. It's like a two-dimensional gas. So you have a lot of sulfate ions moving around the surface without no order at all. But when you increase the coverage, there comes a point where the coverage reaches a critical value, and then there is a phase transition. And this two-dimensional gas becomes something like a two-dimensional crystal. And this is what we call an order, in this case, a disorder-ordered transition. And this disorder-ordered transition is signaled by this very sharp spike in the cyclic voltammogram, which, by the way, is a way of knowing how good your long-range order in your crystal is. So if your crystal has a very long-range order, this means very flat, extended terraces, then these spikes will be very sharp. If your crystal is rubbish, then you will have very small spikes here. And one interesting thing is this is for lithium, sodium, potassium, and cesium. And we, again, go increasing the concentration of the cation. Here, you barely see any effect with lithium. Here, you don't see any effect either. We see some effect if we increase the concentration further, but we stop here. But we know that if we go to more concentrated, we see some small effect. But look here at potassium and cesium. We see an effect here. So I forgot to explain. Here we have this disorder-ordered transition. So here we have an ordered sulfate layer. And if we increase the potential, here we absorb some more sulfate, and the layer disorder. When we have sodium or potassium, this feature here changes quite a lot. You see here, again, we have sharp spikes. We have not looked at this with the STM yet, but I am pretty convinced that here we are having some kind of other phase transition. Probably from this structure here, which only involves, we know that it only involves sulfate and water or hydronium ions, to some other structure where we have substituted the hydronium ions by the cations. And in this case here, in cesium, we also see an effect on these spikes. They go more positive, and the intensity decreases. We also see this with sodium and potassium, but we need higher concentrations. So again, we made the same thing. We plotted the potential of these peaks here and of these spikes as a function of the concentration. So these points here correspond to the spikes. We see that we only see a real effect for cesium. The spikes go from here to here. And this here corresponds to this process here. We only see a real effect for potassium and cesium. And again, we see that the behavior remembers us very much what we saw with cyanide. So just simply graphically, we see that the same model, it's evident that the same model applies to explain the effect of the cations on these voltammetric features. We can explain them with the same model as we use for cyanide. I developed again a model. I am not going to get into this because the model I know that it needs some correction because it's not perfect yet, but I'm convinced that it works. That's why we have not published it yet, because I still have to make some correction here when I have time. But it's evident that it's the same model which is applying. And we can explain the effect just by the fact that we know that the ordered sulfate structure contains sulfate and water molecules, probably hydronium ions. And when you have cations, these cations are going to replace the hydronium ions and affect the structure of the layer. And that we have an effect, which is very similar to what we had with the previous thing. But there is something more interesting yet with this thing. Well, obviously here, when I told before about using many cations, if you are working with lithium, sodium, potassium, and cesium, you are not going to reduce them in aqueous solutions, never, because you have to go so negative that before you start reducing the ions, you will start evolving hydrogen. But if instead of that you use silver of copper, you could reduce these non-covalently attached cations to the metallic state. And if you are lucky, you might have a sandwich. You might have your metal, your cyanide layer, and a metal, bidimensional metal film on top of your molecular layer. And this means that you can then use your molecular layer as an element in an electronic circuit. You can force electrons to pass across this molecular layer, across a group of molecules, and use the electronic properties of the molecules as element to benefit in an electronic circuit. You can, if you are lucky, they might behave as diodes or transistors or who knows what. So we thought of this. We were not the first to think of that. So Kolb already some years ago did something very similar. Instead of with cyanide, with pyridine. So he first immersed a gold surface modified with pyridine in a solution containing palladium, and then he reduced the palladium, and he got these beautiful images. And he could demonstrate that all these bright things, these bright spots here, they are small palladium islands which are sitting on top of the pyridine film. So they are sandwiching pyridine between the island and the metal underneath. But he did not realize that this was possible because you were retaining the palladium ions non-covalently with pyridine. We did the same thing with copper. So here we have copper retained on the surface, and when we go negative, so the black cyclic voltammogram is without copper, and the red one, before doing the voltammogram, we immersed the electrode in a copper-containing solution, we rinsed it with water, we went to a solution where there was no copper, and then we went negative with the potential, and we have these peaks here, very reversible. And when we look at this with the STM, we see this thing here, which looks very similar to this. The only difference is these big islands here. We know that these big islands is copper that has gone underneath. So the system here is not so perfect as this one, because some of the copper goes underneath the cyanide, but we still are making very tiny islands and making sandwich things. And the interesting thing is that here the islands, they are much more similar in size, all of them, than here. And this is probably due to the particular structure of the cyanide-modified platinum 111 surface. So one direction of work now is to try to modify further our surfaces so that we can control the size and the distribution of these islands. We want to have equally sized islands and regularly distributed on the surface. And then we want to look at the physical properties of these islands and at the way that electrons are transmitted from the island to the metal substrate across the molecules. And the other, well, I have forgotten what I was going to say, so maybe later I will remember. Let's go ahead. So the beautiful thing of this is that if you can create these sandwiches, this process can be replicated several times. So you could create, metallize an add layer, then create a new add layers, metallize again, and then you can start playing with using always the same molecule, using different molecules, the same metal, different metals. Some of these metals could be ferromagnetic, so then you can start playing with the magnetic properties and how they affect transport across the molecules. So this gives you a huge play field for doing experiments. But there is another thing here. So here we have seen what I have shown before, that if you attach a metal like silver, let's say a noble metal, like silver, copper, probably also palladium or gold, and then you reduce it, you metallize that layer. But instead of attaching these kind of metals, you could think of attaching non-covalently to your surface metals that can switch from an oxidation state to another one. Suppose that you can attach, let's say, manganese or cobalt-2, cobalt-3, and iron, and you can just keep them retained on the surface and oxidize them to iron-3, and then reduce it to iron-2 or cobalt or whatever. Then you could think of having something like this. You could think of using these surface-retained ions as redox mediators in electrocatalytic reactions. So, for example, oxygen reduction reaction, which is probably the most important one. Some enzymes are very good at reducing oxygen, much better than any electrocatalyst that we have been able to develop. And the thing, all these enzymes, what they have an active center. And all these active centers, they have at least 2 metal atoms. And these 2 metal atoms, they have 2 properties. One of them is that their redox potential is slightly more negative than the redox potential of the oxygen-water couple. Obvious. Otherwise, they would not be able to reduce oxygen. But this is not the only thing. They are placed at a distance at which they can form a peroxo bridge. So they can bind an oxygen molecule with an oxygen bond to each one of the atoms. And they are in a place which is very flexible. So they can change, they are flexible and they can move and change that distance. So once they form this peroxo bridge, they can break the peroxo bridge, separate, and what they have, you have 2 metal-oxygen bonds. Then protons come and you release water. So if you have something very flexible on the surface too, so if you have a lot of cations moving, because you have a 2-dimensional gas, you have some chance that at some moment they will be at a distance ideal to form a peroxo bridge. So you could form a peroxo bridge, then reduce it, you break the peroxo bridge, and you have water.